Hello. How are y'all doing?
Excellent.
Good. We're here to talk to you about transactions. Don, you made it.
I did make it.
No problem with security.
No,
Cool. Is this going to be a habit?
I don't know. We'll see.
Which one of you is naked?
You'll notice Jim never walks away from the podium.
I'll have to remember that.
Yes. I offered, but he said, no, Don, I don't want you to take your clothes off. So I said, you know what that means.
Yep. So, we're here to talk about transactions. Before we get started, I wanted to tell you that Don's previous two talks, 301 and 302, will be rerun on Thursday. There will be some details to follow. Is that right?
Yeah, they're going to repeat 301, WSV 301 and 302 sometime on Thursday because the rooms were too small. Details they're going to figure out later today. So I was just told that.
So anyway, thank you all for coming. We've got some really great stuff to talk to you about. We've been doing some really amazing work in the transaction space for Indigo and for Whidbey and other releases you'll hear about. It's great stuff, and I'm really glad you were able to show up, even if it did mean holding off on dinner a little bit. Now, the first thing I want to get across is what we're going to talk about is simplicity. As you can see from this, clearly we're into simplicity. Okay. We're actually the tiny wee box right at the bottom. That's all we need. Before we start talking about what we built, we really ought to ask about why we care about transactions. Why is the concept important? And the short answer is because stuff happens. When you think about the environment your applications live in, they have to deal with the fact that exceptions and errors and stuff will happen. And today we tend to build our applications so that they attempt to recover from that and attempt to go on. Typically this is done with something like a try-catch block. And when you think about it, inside the application, when I put the try in place, what I'm saying is at this point in time, my application is consistent. And I'm going to do some stuff, and I'm going to put a catch down here. And at the bottom end of that, I'm asserting that my application is still consistent. If I didn't get an exception, everything that happened in here was meant to happen. If I did get an exception, the catch block is supposed to make it all go away. Now, at some level, that sounds like a transaction. Those of you out there who do database work are undoubtedly thinking, well, that's what we do with databases. We do it inside a transaction, and if the transaction aborts, all the SQL statements go away. Isn't it kind of interesting that we have two completely separate mechanisms for that? We have one mechanism that we use inside our programs for lightweight things called try-catch, and a completely different mechanism that we use over here with databases called transactions. There's another interesting thing about this try-catch mechanism. When you think about it, Don was talking about how pervasive object-oriented technology had gotten a couple days ago. And what we do inside the catch block is we take the knowledge of what it means to be consistent and we peanut butter it through the application. Okay? I'm doing this stuff. I have operations I'm doing against objects inside my application. I go to handle an exception, and it's not the object that's responsible for getting back to a consistent state. It's the catch block. What you'd really like is something where the object can help clean up, where the object can help get us back into a consistent state. That's what databases do. That's how transactions fundamentally work. So why don't I do that? Why don't I use transactions everywhere? Now, there have been a lot of reasons suggested, a lot of issues brought up, but they all fundamentally come down to one of two things. One reason is because they're really hard to program. If I want to create a transaction that's just going to surround 4 or 5 lines of code, I've got to go do a whole bunch of stuff. I've got to go use some interfaces that aren't terribly easy to use or easy to get my head around. Inside the objects, I've got to use a whole set of interfaces that definitely are not easy to get my head around. And it's just hard to do. At the other end is the fact that even if it was easy to do, it's slow. I need to be able to do this millions of times a second. With today's transaction systems, I can do it thousands of times a second. And for all the reasons you hear, they tend to come down to either it's too hard to program or it's too slow, or both. And one of the conclusions we've come to is that these are statements about the implementation. These are not statements about the concept. These are myths due to the sorts of implementations you've been working with up until now. And our goal is to destroy that.
With a sledgehammer.
Absolutely. What we want to do is to make you more productive, make you have a simple, common mechanism for keeping your applications consistent, and do that by providing a single interface that scales up to high-end database applications, out to other vendors, and scales down so that if I'm not doing very much, it doesn't cost me very much. I can actually use transactions around really lightweight objects. And I want to do it with a set of interfaces that are sufficiently easy to use and sufficiently available and pervasive that I can assume that I can do it ubiquitously, that anywhere that I'm trying to do things, I should be able to assume that there are transactional resources available to me, or that it's easy for me to construct them. And that's fundamentally what we've been doing with system.transactions. Now, I want to walk you through a little bit of a diagram about what system.transactions is. You'll see this diagram in various forms throughout this presentation. We're going to delve fairly deep into it. What we're doing is we're adding a new managed layer at the top, the boxes you see in yellow. These are both simplified interfaces that you write to and implementations and features that we use for achieving some of the scaling and feature mechanisms that we're making available to you. These themselves are also layer on other features that you either already know and deal with, such as the blue boxes, the Distributed Transaction Coordinator, or on features coming in future releases, such as Longhorn, which include things like the kernel transaction manager and the Windows logging services. The fundamental message, though, is that you code to the very top. You code to system.transactions. All the rest is an infrastructure that is able to adjust based on what you're doing. Now, it's really important. This is a managed code interface. This is a single managed code interface. We're bringing transactions as a basic concept into the CLR. It's not goop associated with anything else. These are simple standalone transactions. It's a single interface you code to. It's a single set of features. A lot of it's beginning to arrive with WIDBE. And we will use this to both deal with the interface issues and with the performance issues. I'm going to start by talking through the interfaces. Let's deal with myth one, that it's really hard to use. In system.transactions, you see a column on your left. This column of 3 boxes represent 3 separate layers we're providing for application programs. There's a very basic layer we're providing at the bottom that we call manual transactions. Manual transactions are really tactile. You can create a transaction. You can go extract one out and carry it around. You can go hand it to a resource manager. Or you can go say, I want to commit this. But it's manual in the sense that I have this object I carry around and I do things with. At this layer, this is the layer that resource managers will work at. this also contains some primitives that we're going to use later on that allow me to place a transaction into the execution context. But that's manual transactions. It's actually fairly simple in its own right, but it is tactile. So layered on top of that is a fairly lightweight thing we're calling transaction scope. Transaction scope builds upon this by allowing me to simply declare, I want a transaction that starts here, and I want it to end here. Typically in a C# program, you use it inside a using statement. And it's a statement of intent. I need a transaction from here to here, and if I get to here and I'm not happy, I need the transaction to abort. It's kind of like co-entered service domain.
Yes.
Without any of the complex goop. It's just about transactions. Now, we expect that for most standard programs, that's the interface they'll be using. That's the one that they would primarily work through. With Indigo, we're extending this, we're integrating it in by adding on top of this a set of attributes that Indigo will offer for service methods that allow the service method to make statements about its execution context. Does it need a transaction when it's running? That's an inward statement for itself. It can also make outward statements. Do I want a transaction to flow in? Will I accept a transaction? Am I willing to have one flow out? That layer, those attributes are themselves layered upon this transaction scope concept. But what we have at the bottom, we have a very simple primitive layer that I carry things around with. Layered on top of that is also something that fundamentally is quite simple, that simply lets me say they go from here to here. And then on top of that, we allow you to say, inside the method, there has to be a transaction before I get called, or there can't be a transaction before I get called. And it's these three layers that for the application program we believe makes using transactions very, very simple. Trivial, I would say. Now, I'm going to walk you through, just briefly, a little bit about the object model. Don's going to show you in quite a bit more animation than I will, just after this. But at the very bottom layer, let's start with manual transactions. What you see is pretty much all there is. At the heart of this, on the left, is this iTransaction object. And this is the thing that I carry around. And I can use this to give it to a resource manager so it can enlist, and I can use it to roll back the transaction. There's a special form of iTransaction called iCommittable transaction that's derived from that. And that's the form that you get when you create a transaction for the first time. And with that, you can also commit. But it's basically this object you get and you carry around. With that, we have a transaction class that's got two static methods. And I use that for creating a transaction, and I get back an iCommittable. And then there's current. That's the thing that I can stuff an iTransaction reference into to make it part of my execution context. And for most applications, even at the manual level, that's all they will ever use. The stuff on the right, the transaction manager bits, are if I'm trying to do something fairly advanced where I'm trying to select a specific transaction manager that I want to be managed by. 99% of the applications will never care about these two objects. For the application, even at the manual layer, it's just those three. And I think probably the best way to show this is to let Don write some code.
Great. Thanks, Jim. Oh, wait, this is one of those rooms. Hold on. Hold on.
Oh, that looks like code.
Yeah, see? Watch. It works.
Amazing.
I just can't use both hands when I do it. So, I've got a machine here with The system.transactions DLL installed. We're going to write a little bit of code. So notice I've already brought in the namespace for system.transactions. And let's get started. The most basic thing I can do is call transaction.create. And transaction.create has several overloads. The default, or the no-arg overload, reads in the default isolation level from config, as well as the default. I think the timeout is infinite by default. And the default isolation level, if not modified in config, is serializable.
Right.
There's obviously overloads that allow me to pass in a time span. There's also one that allows me to pass in a Gymundo data structure that I can fill in as many pieces as I need. But for our purposes, we'll trick Visual Studio into passing no arguments. The result of this thing is I can pass this into an iTransaction. And I can then, when I'm done with that, call rollback if I want to undo the work I did under the auspices of this transaction. Or you'll notice there's no commit call. Right? And the reason for this again is the transaction I got from create, I want control over who calls commit. And so what I typically do is I go ahead and use the iCommittable transaction interface, which does have a commit method. But then if I'm going to pass this to someone else, I call tx.clone, which, as you'll note from the IntelliSense, if you can actually read that, returns a vanilla iTransaction, which again has no commit. And again, the fear is I call create trans, begin trans, and I somehow get this over to Jim. I want Jim to do work, that's charged against my transaction, but I don't trust him to not call commit. So by having a clone that commit is disabled on, I don't have to worry about handing him my transaction. Yes, he can enlist. Yes, he can tank my transaction, right? By enlisting like a normal transactional resource. That's what I get. I don't want him artificially doing a successful commit from out from under me. That would scare me.
I would do that.
You haven't done it to me yet, Jim, but that's only because I've passed you clone transactions.
Ah,
That's the way our relationship has gone so far. It's that whole service-oriented boundary thing.
indeed.
Last time I checked, neither one of us have violated each other's boundaries.
Not that I know of.
Okay. There was that time when you were asleep, but. So we've seen that there's iTransaction, which has rollback. It also has the enlistment routines, which we'll actually use in a few minutes. And I call commit to be done. Often what I want to do is store a version of this transaction in transaction.current. Because the way we propagate transactions to resource managers. So if I use like a database connection or a queue or some of the more, the more interesting scenarios like a transacted collection, right? The way that transacted resource knows what transaction to use is through this ambient transaction, which is exposed to the transaction.current property. So what I can do is say transaction.current equals tx.clone. And again, I'm not quite sure what code is going to run between those two lines. So because I don't really know what's going to happen, I don't want someone doing a successful commit until I'm ready to do the commit. If they abort, well, hey, they can abort anyway. But they can't get the work done until I'm ready. So I put a clone in there, which basically is just a second GC object that you can't commit on. So that's the deal. I feel, you know what? I want to compile it. I want to run it. Yes? Are you okay with that?
Absolutely. Let's do it.
Cool. So, notice it takes almost no time for the app to start up. There we go. So I call transaction.create. Watch. See? Wasn't that fast? That was super fast, wasn't it? I then assign a clone of the transaction into the ambient transaction reference. And then, because I've decided to do a commit, I go. You know, Jim, Is there any more you want me to do, or is that sufficient till we move on? You want me to do a list of resource or something?
That's sufficient for now. I think we'll
Okay.
come back to this one.
Great.
Okay.
Oh. No, you stand there. Ready?
All right. So we built on top of that. So we built this transaction scope. Transaction scope really is just a very simple demarcation mechanism. The transaction scope object is just an object that takes, typically it's going to take a set of options. Those options are statements about what I want in my environment. And you can see them at the bottom. We've got some helper ones that kind of look like the COM+ ones. I can say, I don't want a transaction running no matter what the state was. I can say I want a transaction running, and if there was one, that one's good enough for me. I don't need a new one. Or I can say some other things. But what I do is I say, that's what I want here, and that's going to start the transaction. I'm going to do my work, and then I'm going to call this consistent thing, this consistent property that you see up in transaction scope. And if I set it to true, that says, I'm happy for it to commit. And then I'm going to let the thing dispose. And that's going to proceed through the commitment. Now, there actually isn't anything more for me to say about that. That's all there is. So, we snuck a declarative model in.
Yes. That's what it looks like in Indigo.
That's what it looks like in Indigo.
So shall we code some?
Well, that's code. No, this one. There we
Sweet.
go.
Thanks. So I can rip this code out by doing this. Transaction scope S equals new transaction scope. And there's several ways I can initialize this. I can either, if I have a transaction that someone handed me, perhaps as a method parameter, but I still want to get this declarative, commit or abort based on the outcome of the block of code, I can actually give it an iTransaction. The more normal expected use is to use a transaction scope options. And here, I can either use the individual bits to control independently the propagation versus the whether I have one of these or not. But the expected usage is people got used to these attributes in EJB and COM+, and you know what? I type them every time too.
Yep.
So some habits die hard. So what I've said here is the block of code that is delimited by these two curly braces needs to have needs to have an ambient transaction. If there's already an ambient transaction, we'll use it. If not, we'll make a new one. We'll talk about the other subtle differences in a second. This commit call goes away. And instead, what happens is the using statement sets up a try finally handler. When I leave the block, one of two things will happen. Either an exception was thrown or it wasn't. What I typically do is at the end of my block of code, I set the consistent bit to true. This is kind of like enable commit from COM+, if you ever use COM+. And so what I'm saying here is, and by the way, the default for consistent is false. So when we enter the block, we're automatically not consistent. We have to take an action to be consistent. If I don't make it to that last line of code, then an exception was thrown or I did a premature return out of the method, which is also possible.
Right.
If I don't make it to the end, then what the dispose routine will do in the transaction scope, in the finally block, is it'll do a hard abort. It'll do a force abort on the transaction, guaranteeing that anything that happened against transactional resources gets undone. If I get to the end of this block, then I hit the consistent bit. What the dispose does is it simply looks at the consistent bit, which defaults to false, and I have to explicitly get there to set it to true. If it's true, then what happens really depends on this guy. If the initialization of the scope had to put a new transaction in the ambient property, then I was the guy who created it, I'm the guy who closes it, so a commit will be issued. If there was already a transaction up in the ambient transaction, then I'm just doing a subordinate piece of work. And so in that case, we do nothing. The dispose just says, phew, we made it. We don't have to do anything bad, but the choice of committing is not my choice. Because again, this notion of the guy who calls create is the guy who calls commit turns out to be a very, very important premise, and we do our best to make sure that's the way everything works. Right? And if we screw it up, it's because we screwed it up, and hopefully we'll fix it before we ship it. So that's the way we use transaction scopes. And again, another thing to note here is if the new transaction scope caused a new transaction to be created, that is, if there was no ambient property and a new one was created on my behalf, even if I set consistent equal to true, that doesn't mean the transaction will commit. What it means is my code will implicitly issue a commit request. But it's entirely possible one or more resources I was using got tanked, and the overall the aggregate transaction will abort. And so what will happen is, if I want to find out the outcome, I would put this guy into a try-catch block. And catch the transaction abort exception. Does that make sense? So, and at this point you might say, well, boy, maybe I should have just used the transaction explicitly, and maybe that's the case. The goal, though, is to write code that just uses transactions and doesn't have these try-catch blocks all over the place.
So why don't we try something, Don? Why don't you try writing a method in the middle that also requires a transaction?
Writing a method in the middle, writing some code in the middle that also needs a transaction.
So come up with a method F.
Okay, hold
That
on.
we're going to call in the middle. That also uses a transaction.
Like this? Mm-hmm. And then I do a transaction scope inside?
Yep.
You know, everything in this namespace begins with a T. It kind of makes the
Funny
intelligence.
that.
Yeah. And what value do you want me to pick?
What value do you feel like putting?
Well, I always put this one, because I don't have to think then. Got it? And so now I bet you want me to call that from in here.
Yeah, well, okay. So what do you think that'll do?
Well, more importantly, what do we think our customers think it will do?
Yes. It's going to abort. You need to set consistent in the F.
They're listening.
Yes?
That's one way I could have solved the problem. What's another way, Jim? Do tell. What happens if I actually didn't do this? What happened, correct me if I'm wrong, is the outer scope's transaction was inherited by the inner scope. Because the inner scope never set the consistent bit, we tanked the transaction. Oh well.
Right.
I could have said transaction scope options. Oh, that's so pleasant. I like that. That's a nice ring. Normally I get pissed off when people let their phones ring, but that's so nice. In fact, give us your number and we'll all call you all day. So, had I done this, which basically said, I don't care what's in the ambient transaction property, make sure it's null before I run. Had this happened, that would be okay. This wouldn't have hurt the outer scope. Similarly, if I had done the requires new, here what I'm saying is, again, damn what's there now, put a new one in there, push a new one into that slot for the duration of this scope, and then when I leave the scope, pop it back in. Does that make sense? They nest in the lexical stack frame world. They are not nested transactions. Just like in COM+, just like in enterprise Java beans. In fact, Jim, correct me if I'm wrong, just like in virtually every production commercial transaction processing system except for perhaps one, we do not support nested transactions.
They are basically supported very, very rarely, yes.
Yes. What is the one system on the planet that supports them?
Actually, I don't know that I know.
Oh, okay. Pardon me?
Yeah.
Jim, who supports nested transactions? The CMU system. Thanks, Jim. So great. I often have Turing Award winners in every talk to just back me up like this. It's a great thing. Great benefit of working at Microsoft. So these are not nested transactions. The outcome of the two transactions is completely independent. The inner transaction could abort. Well, actually, let's be clear. If the inner transaction, the one in F, were to abort, what's going to happen is, because I don't have a try-catch around the call to F, I'm never going to get to be able... So this call site isn't doing anything to protect itself.
Right.
So because that exception would propagate out, I'm never going to get to here, which means I'm also going to abort. But that's actually just an accident of the way the code is wired up, right? The two transaction outcomes are completely decoupled. It is, if the inner one commits, that commit is not pending based on the outcome of the outer transaction.
Exactly right.
So the nesting is not in the transaction scope sense. Got it?
Yep. Oh, there we go.
Did that.
Indeed. So what we've tried to show you is that actually demarcating a transaction is now very, very simple. As you see, it's two statements and a couple braces for most people. And internally, trust me, we've tried to make the scoping mechanism as lightweight as possible. And in fact, the scoping mechanism, as should be clear from this, only discusses the transactional aspects. There's no other goop involved. And in our view, that really, for the application, destroys myth one. It isn't actually very hard to create a transaction. And while that's really great, it's completely pointless if it's still slow. Now, in the past, the interfaces that we've offered you, the structure we've offered you, the mechanisms we've offered you, have been very much a one-size-fits-all strategy. The moment you said create a transaction, we created a transaction that was capable and built for the most maximal set of things you could possibly do with it. It was built for the heaviest weight, most distributed structure that you could possibly throw at that thing. And while that was really great because you could do lots with it, you'd better be prepared to do lots with it because you were paying for it. What we've done is we've refactored it internally. Inside system.transactions, there's a completely different structure of factoring. And what we instead have now is a structure where we really work very hard to give you a pay-for-play model. It starts out with a very lightweight structure, and then as you try to do more things, it migrates to heavier weight transaction coordinators. And key behind this is we've actually brought together 3 different state machines. There's the LTM, the Lightweight Transaction Manager. In Longhorn, there's the KTM, the Kernel Transaction Manager. And then there's also DTC, the Distributed Transaction Coordinator that you've had for some time. And it's finding a way to manage the relationships between them that's key to a large part of our performance story. Now, if we look at this slide, this really lays out the 3 underlying components. Now, note that you just write to system.transactions. You notice that in none of these examples was there any goop around what transaction manager you were using or who controlled it or anything else. Out of interest, how many people think that the examples you just saw were run by the Distributed Transaction Coordinator, DTC? Good. How many people thought they were run by KTM? How many thought they were run by LTM, the Lightweight Transaction Manager? Exactly right. What we have is we've got 3 different transaction coordinators. We always start with the lightweight transaction manager. The lightweight transaction manager runs inside your app domain, and it only knows how to do a few things. It knows how to create a transaction. It knows how to handle enlistments, local enlistments. It knows how to commit a transaction. It knows how to do those three things extremely quickly. You can create and commit an LTM transaction in under a microsecond. However, it also knows, most importantly, how to do one further thing. When you make a request to it that it can't handle, it knows how to package up everything you've done to this point and hand it off to another transaction manager. In WDB, the transaction manager it will typically hand off to is the distributed transaction coordinator, because that's the fallback that we have. As we move towards Longhorn, you should expect that there will be cases where we will migrate to the kernel transaction manager because it has improved performance profiles. But the basic structure, the basic factoring, the basic direction we're going after is one where we start out with the least overhead transaction manager for what you're doing, and we attempt to maintain as low an overhead profile as possible as you do things to it. For you, we offer a single interface that gives every appearance of being fully capable of doing distributed transactions, and in fact is. But the component that owns, boy, that was anthropomorphizing, wasn't it?
Yes, it was.
Yeah, okay. The component that owns that transaction will change depending upon what you're asking it to do. So it starts out in the LTM, and in this picture, it will either migrate to the distributed transaction manager or to the kernel transaction manager. Now, I actually lied, because there's one other thing it can do. There's one other target. And this is an example of sort of what I was trying to get at with we will strive to keep the overhead profile as low as possible. One typical use case is you're doing a bunch of local stuff and you invoke SQL. And today what you do is that means you go to DTC. Or it means you do something completely different and you use SQL on a completely separate API and path. What we really want to do is offer you a single way of doing this while getting as best a performance profile as possible. So let's take a look at what that means. I start out, I've got my app, and it creates a transaction. And that's being managed by the LTM. I then have a little local volatile structure, and that enlists in the LTM. The LTM still manages the transaction. I haven't done anything that it can't do. If I said commit right now, LTM would manage it, it would commit, life would be great. I then go and just do a connection to ADO.NET. Now, ADO.NET is going to talk over to SQL. But ADO.NET in Yukon, with Yukon, knows about a set of interfaces that the LTM offers that allow it to say, I actually want to take ownership of this transaction in a semi-revocable manner. So it goes through to SQL, and we do what's called a single-phase delegation. And the ownership of that transaction moves over to SQL. Now, if I say commit at this point, I'll still first go to LTM. LTM will first deal with its local volatile resources, and then the commit, assuming that everybody voted yes, the commit will be transferred over to SQL. So I've managed to start a distributed transaction. System.transactions, just a normal thing. I've managed to invoke some non-SQL resources. I've managed to invoke a SQL resource. And I've never actually promoted to DTC in this. And now I go do something really awful. I go to marshal it. I want to go talk to somebody else completely random. And in that case, I really need a full distributed transaction back. I've just gone and done a heavyweight thing. And this is why I said it's semi-revocable, because as part of this interface exchange, LTM is able to reach back into ADO.NET and say, I need a full-scale transaction because I got to marshal it and send it somewhere. And that goes over to SQL, and at that point, and that point only, do we finally promote to a full distributed transaction coordinator. And I get back a full heavyweight transaction, and I'm able to do the marshal. And at this point, if I was to commit here, start out, the commit first go to LTM, I deal with my volatile resource, and then it would go on to DTC. Okay. Now that was a fairly sane description of some agility. Don said he had some tricks he wanted to show. I'm not completely sure what to make of that.
Well, let's just see.
Okay.
So the first thing I want to do is,
I'm sitting back here.
okay, I want to take the code, a simpler version of the code we just looked at. So this is exactly where we left off. I took the body out of F because there's really nothing interesting. And we just have a single transaction scope that starts up and away we go. So what I'm going to do is go ahead and run this thing in the debugger. And I don't need this anymore. So notice that I've got the distributed transaction coordinator monitor running down here. Right, so we can see what's happening. And I mean, the punchline, you've already seen the punchline. There have been no distributed transactions. You know, distributed transactions have been harmed so far in this demonstration. And certainly, I can go into my program and call F, consistent true. DTC never got invoked. What I'm going to do, ooh, what was that? Who knows? What I'm going to do is inside of F, I'm going to call this function, which I wrote, called use volatile resource. And what this is going to do is it's going to touch a transactional resource that has no durability guarantees. That is, it's a completely transient in-memory phenomena. If the system crashes, it makes no guarantees that it will be recoverable after a system failure. And so for, if I have a transacted collection or a transacted data structure, as long as it has no on-disk image, it's going to be a volatile resource. And so I can use a volatile resource. I can use as many of them as I want. And, boy, that's going to be annoying. So we start our transaction scope. And notice that even as I use these volatile resources, right, those are triggering enlistment calls, which we'll look at in detail in the next demonstration. But there's a whole bunch of two-phase commit wiring happening in each one of those calls. None of this has caused the DTC to get involved because the LTM knows how to implement two-phase commit. It's not rocket science, and we can do it pretty easily and pretty quickly. So we can do all of that in memory, completely in managed code, no disk, no I/O, no interop either, because it's all 100%. It's just, it's just IL. And again, I'm able to commit. Nothing happens at the DTC level. Now let's look at a few other things. If it only takes one of these in the punch bowl, if I use a durable resource, get out of there. Emacs never does that to me. So I'll go ahead and run it in the debugger up to that point. And notice the first time I touch a durable resource, like a database, a message queue, the file system, the registry, anything that has persistent store, LTM says, it's not my job. I don't have that capability. And because I'm not on a Longhorn box, this is just a Windows Server 2003 box with Whidbey on it. What's going to happen is as soon as I do the enlistment, there's no KTM, because KTM is a Longhorn feature. It's not available in Windows 2003. The only thing I have to promote to is DTC. So as soon as I step over this line, the durable enlistment caused DTC to get involved. Make sense? Cool. And then if I let it go, oh, Jim. Scheitze. Excuse me. Here's what happened. The resource manager, this is a terrible thing to have happen. The resource manager was running in process. We got in the two-phase commit. The DTC tried to do the commit. It did the prepare. The prepare came back. All that was fine. It tried to deliver the
Commit.
the commit notification to the RM. But of course, I shut down the app domain before he had a chance to respond. So, alas, we have a wedge transaction. None of this will work. Jim, this is what happens when we use live bits. That director thing we were going to use with the flash and all that, that would have been much better.
It would have been much better, yeah.
Yes. Yes. So that's one thing I can do with transactions. Another thing that's actually pretty interesting to take a look at, as nasty as that is, God, I can't believe.
That's how we should have done the demo,
What?
with DTC stopped.
Yes. Yes. So the other thing that's somewhat interesting to take a look at is, in general, the transaction object I've got is for use within my app domain. We have support for any number of ways to take that object reference, the transaction reference, and move it elsewhere. Oh God, it comes back.
Yeah, it does come back. That's why it's durable.
Oh, of course, it's a durable resource. Duh. Hang on. Well, now you're challenging my...
You ought to be able to say forget or abort, I would think.
I can forget it, I believe.
There you go. You've just corrupted the user's data.
Yes, I have. Thankfully, I'm the user in this case. I wrote that code, so I deserve what I get. So the other thing that Warren's talking about, though, is we have a variety of ways to take this transactional object reference. It's just an in-memory, object reference pointer, and turn it into different forms that can be used in different contexts. So, for example, if I want to take this LTM transaction reference and interop with some ES code. So, for example, today, like on this box, I don't have a version of ADO.NET that knows to look in transaction.current because this is a very early, barely working build right now. So if I wanted to use the transaction that I just created with say, SQL Server, SQL Server does have a way to enlist against a DTC transaction, but it won't take the iTransaction I've got here. So we have this interface called iTransaction Marshall. Which I can simply cast for. And this gives me a Marshall routine. And to Marshall, I basically say what the form of reference I'm looking for. So if I say type of system.transactions.olatx transmitter receiver Marshall transaction, that gives me a serializable object that will write out a byte stream that I can then pass to other DTC applications as a serialized transaction. There's also the traditional import-export model, and also the one that actually is very useful here is if I just say OLATX transaction, it will give me a ES style, .NET Enterprise Services form of a transaction, which I can then pass to the old world of ADO.NET that I have on this box. Now, by the time we ship WIDBE, WIDBE will support transaction.current and system.transactions. But we're going to bring WIDBE into the new world. I'm sorry, we will bring ADO.NET into the new world. Invariably, you may have some transactional plumbing out there that you're not really going to want to go off and tweak necessarily. So in order to allow that stuff to play in this new world, we have the ability to move back and forth. Again, this is the WIDBE build. So the WIDBE build doesn't have support for WS transactions. But in the Longhorn builds, another one of the Marshall types is I can ask for a WS coordination context. And what it will give me back is the XML representation of the header that I can then put into any of my SOAP messages to send around. So when I actually want to propagate one of these transactions, especially when I have trust and I have latency, when I have bounded latency and reasonable trust, I can propagate this transaction if I want across a web service boundary to WebSphere or WebLogic or whatever else is out there. So the way I do this coercion of the in-memory transaction to this externalized form is by using the iTransaction Marshall interface. So there. Tricks are done.
Okay.
And I promise not to lose any transactions like that again.
That would be good.
Yes.
The active marshaling brings in DTC.
The active marshaling brings in DTC. I don't know. Let's find out. I do know. I'll just say the answer. Yes. I could type, 2 lines of code, but yeah, what happens is LTM tries to avoid any of that stuff whenever possible. But if you come out and say, I need a DTC transaction or I need an OLATX transaction, yeah, what we interpret that is yeah, you want DTC, and we'll go grab it for you.
Yep.
Cool.
Okay. So are we done? All this is cool. But getting the app interface is simple. Getting a transaction model and an infrastructure that lets me have transactions that are very, very lightweight whenever possible is really useful, but not really useful if I can't have resources. Because at the heart of this, I've got to have recoverable resources that I'm working against. So the other arm of what we're doing is to work on making it much easier for you to build into your systems recoverable resources, to really bring the idea of a recoverable resource out of the database. Now, this is one where really tradition has said this is really hard to do. Okay? God knows in DTC, I looked at the interfaces and I couldn't figure out what they were about. And I thought I knew what a resource looked like. Now, we've done a lot of simplification, but there's still this belief that there's something really complicated about it. And in a way, when you think about it, it's really kind of ironic, because it's only a couple message exchanges or only a couple notification exchanges. I've seen forms that are a lot harder to write. Okay? And people do that all the time. So what we're trying to do is we will be building in interfaces that simplify the ability to engage in a transaction and provide infrastructure that help you with the other aspects of building a resource. Now, as we go through this section, we're going to talk about really 4 main aspects of it, or 3 main aspects of it. The first is just what it takes to participate in the transaction. As far as the transaction, as far as system.transactions is concerned, that's all there is to being a resource. The fact that you can participate in the outcome and you get to hear about the outcome. So we're going to start with that. Now, as you build up more complicated resource managers, there are 2 other things that you're probably going to be interested in having. There are 2 other tasks that typically you're going to have to end up doing. If I'm building a durable resource, typically I'm going to end up needing a log of some sort. I'm going to need something that allows me to put stuff off to the side so that I can get back to it if everything didn't quite work out the way I'd hoped. And we'll be bringing into play with Indigo a set of interfaces under system.transactions.log that make that easier to do. And then the final arm is if you're trying to support multiple accessors, again, there's a common bit of lock management logic that you're going to end up needing to do. And we're also bringing supporting infrastructure in place for that. So we're going to talk through all 3 of these, and we're going to start with what it takes to just simply participate in a transaction. Now, the first thing to be aware of is that this participation, this identity, this ability to vote, we assume it's an asynchronous relationship. So there's a pair of notification objects that get exchanged. There's one you write, there's one we write. The one you write is based around I-enlistment notification. It allows you to say, call me here when you want a vote. Call me here at prepare. Call me here at commit. And the way that you decide to participate is you take your enlistment object and you call us at an enlist call, either a volatile enlist or a durable enlist. And that tells us that you want to participate, and we'll call you back. And when you return from the prepare call, that means absolutely nothing to us, because it's an asynchronous relationship. You can return, and that doesn't mean anything for moving the thing forward. What's important is that we also hand in to you on these events our notification object, which either is I preparing enlistment or I enlistment. And that's what you call back when you're done. And that's really how the exchange works. It's really very, very simple. And if you're building a single-purpose, single-user, volatile resource, that's all there is. That is the definition of the resource as far as we're concerned. Shall we build one?
Yes.
Okay. So let's start with that.
You didn't know you'd have to work this hard.
No, I didn't.
You didn't know there'd be physical labor involved. So what I'm going to do is implement a simple resource that does enlistment. So class my resource, public void use me. And what I'm going to do is, inside this use me method, I'm going to enlist on the transaction that is in the ambient transaction slot. And so to do that, I'm going to need an enlistment object to wire up to the transaction that might be up in the transaction slot. So to do that, I write a new class, public class my enlistment, and I implement I-enlistment notification, which is the resource side of the two-phase commit protocol. And in this interface, I have 4 methods: public, void, commit. Actually, hold on. Yes. And here I get an I-enlistment as an argument. So I'm doing the phase 2 part first because it's easier to type, as you'll see in a second. So phase 2, which happens after we know the outcome of the transaction, all we have to do is let the participants know. And the way I will be informed is one of these 2 methods will be called, and only one. Then there's this third method, prepare, which takes 2 arguments. It takes an enlistment that happens to be of type I preparing enlistment, and it also takes a binary cookie, which we call the recovery info. And this is probably the most important method in the whole suite. What happens here is when the application decides it wants to initiate a commit, we'll get a prepare call. And in the prepare call, we're given this enlistment object, which is the async point we use to let the TM know how we feel. But also, we're given this blob. And this blob to us is opaque, but it means something to the transaction manager. And if I'm a durable resource, I'm expected to take that recovery info, squirrel it away into a file or with the rest of my state, such that at recovery time, when I come back after a crash and need to know how did this thing actually turn out, I can come back around and say, this is what you told me was the opaque identifier for this transaction. What do you think? Can you give me back the information? And transaction managers may put any number of pieces of goop in there to make the recovery process as fast as or to tune the performance of recovery as they would like. So the fourth method gets back to one of the optimizations that Jim alluded to in that diagram where we showed the various enlistments and how things got promoted. there's an optimization called single phase enlistment. And if there's only one durable resource, that is, there's only one piece of code that has any kind of log involved or any kind of store involved, we actually have an optimization where we'll delegate the application commit or rollback down to the single phase resource manager. And in general, this works out just fine. There's an interesting issue, which is there's a nasty condition where if I issue a single phase commit and we crash, right? We have different crash characteristics between the resource manager, which might be SQL Server. In fact, SQL Server implements this optimization, and my application. It might be the case that the in-memory code can't actually report what happened because we lost connectivity to the actual resource manager. So if there's a single phase enlist, that's the only time we'll ever get this. We'll get an in doubt. And we will not be seeing one of these calls in this talk.
Well, I trust.
Since everything is running in a single app domain, if we see this, then run out screaming.
Yep.
So let's go ahead and do the deed. Right off the bat, if I were to enlist this particular object with the transaction, we have some problems. Because what's going to happen is application is going to try and call commit. We're going to get this prepare, and we're never going back. We return control. We let the thread unwind the stack. That doesn't convey what our vote is. Again, we assume asynchronous is the default here. So I actually have to take an action either inside this method call or somewhere else, perhaps on another thread, but I have to call e.something. And the three options are force rollback, which means you want me to prepare, there's no way I can prepare, screw this transaction. Or I'm prepared, but I care how things turn out, which is kind of the usual. In the case of a successful transaction, this is the usual case. It is possible, however, that I don't really care how things turned out. I have no undo state to worry about. I was a read-only resource as far as this transaction was concerned. All I really needed to know was it would be okay for me to hold some release a few locks. So in that case, what I would do is call enlistment done, which says the vote is yes, and don't bother to call me with phase 2, because I really don't care. But since I want to see it work, that is, I want to see the entire state machine, I'll go ahead and make the call back to the TM, and I'll do it just on this thread because I'm here, and we're done. I also, and you'll note that when we had that highly embarrassing transaction that got stuck in DTC, it was because my commit call never had a chance to call back because we let the app domain unwind before my in-memory resource got a chance to do its magic. So I'll do this here, and I'll do this here. Cool. So I've got my enlistment class written. Now all I need to do is do an enlist. And that's pretty easy. So I do transaction.current, which is the way we convey transactions across boundaries. I'll do a volatile enlistment.
Sounds good.
And I make a new myEnlistment. And then I pass a second parameter which says, if during prepare I decide, what I'm going to do now is actually go talk to the file system or go talk to a database, and I want that work to enlist on the transaction, we have a little bit of a dilemma here. Because during prepare, it's a little late to enlist because we've already started the two-phase dance. And so there's no way I would be able to get any new work added to this transaction. So we have this parameter that during enlistment you can say, at prepare time, I may need to enlist something new. And when we do this, we actually, I'll show you how the state machine differs when we do this. So I don't need it for this demonstration. Okay. So I do that, and so we're set. So to use this thing, I'll go in here and say new my resource dot use me Since I don't use the thing for anything else, I think this is sufficient. And let's go ahead and try and compile this thing. Great. And let's set some breakpoints. So I'll set breakpoints in the enlistment routines. I'm sorry, in the notification routines. And I'll go ahead and set a breakpoint in use me. So let's let it rip. So I'm inside the use me method. We haven't done any durable enlistments, and because I'm only enlisting as a volatile resource, my enlistment will not force the LTM to promote. So as soon as I do this, notice there's no DTC activity. Right? And I'll go ahead and let it go. We now bring a durable resource in. There's a bit of a lag in the UI for DTC Manager. Notice that in the status of the transaction, right there, you'll notice that the status of the transaction is it's active, which means there have been no attempts to call commit or rollback. The transaction can have new enlistments happen at the DTC level. We have no idea what's going to happen yet. Now, watch what happens when I go back to my code and try and leave the block. So I just tried to leave the block of the using for the scope. So obviously, we're in the middle of a commit call over on the app code. And we're in phase 1, so we see we're preparing rather. As soon as I let go, everyone will get a chance to vote. And because everyone voted OK, we're now in the committing phase. And again, I'm given the notification. This is the commit routine. I'm now told what the outcome is. And the transaction plumbing will keep state around to make sure it can always report back. Actually, in this case, because I'm volatile, if I were to not call e.enlistment done, there's no durable residue from the transaction being kept on my account. Right? So let's go ahead and let it go. And away we go. Let me just show you one slight difference that I think is pretty interesting and important. When I did the enlistment, I could have enlisted as a durable resource, which I'm just not going to do because we only have so much time in a day. But I could have said, I need to enlist during my own prepare. And this was actually a hack put into DTC for IMDb, which was a feature we never shipped in Com+. Before it became a popular Internet Movie Database website, IMDb was the in-memory database, which was an OLEDB cache. And one of the things it did was it allowed you to do operations against this OLEDB provider. And then when we went to go commit the transaction, only at that point would we push the changes out to the actual SQL server or whatever the data source you were using was. So we're taking advantage of that in system.transactions by simply saying, look, when you do the enlistment, let us know whether or not you need to enlist or not. Originally, I said, no, I don't need to enlist. So when I was in my prepare call, as far as DTC was concerned, we were in preparing. Right? We were already, the dance had already begun. There was no turning back. Now, because I've said I need to enlist during prepare, notice that my prepare call is being invoked while DTC thinks we're still active. So as far as DTC is concerned, we haven't actually begun the two-phase commit. And now, because I said true in that enlistment routine, I now have the ability to go off and make a database connection and allow that database connection to participate in this transaction. Or go off and talk to TXFS, or the transactional file system, and do some I/O against files that will, again, be enlisted against this transaction. Cool. And yeah, of course it all works fine. I'm ready to.
Are you ready to?
I need more PowerPoint. I have not had enough PowerPoint in my life today.
Okay. Not really.
Yes. Quite. Yeah. Every single piece of code we have shown you is a WIDB feature. It does not require longhorn or shorthorn or midhorn. All it requires is WIDB. Now, when you have longhorn, the extra benefits you get are indigo. Well, actually, even indigo doesn't require longhorn, but WIDB's ship date is not necessarily the same as indigo. right? So the declarative transaction attribute and the log stuff we're going to talk about, all these are Indigo features. But the core stuff, every piece of code I have written for you does not require Longhorn, nor does it require Indigo.
So you get this and then it gets better.
Yeah,
Correct.
yeah. This is a min bar. This is above the min bar.
This is above the min bar. We're now actually moving into things that we're going to talk about rather than show you, because among other things, it's showing up in Indigo. Among other things, we're almost done to 4 minutes. Cool. So, as I expand out, as I said, if I look at the other sorts of resources that I would want to build, if I look at the other sorts of problems I'd want to deal with, sooner or later, I'm going to want to have a durable resource. And typically, when I go to build a durable resource, I need some way to store stuff off to the side. Typically, that involves building a log. Typically, that log implements a write-ahead logging protocol, it implements group write, and it's highly performance sensitive for me. Typically, I have to build a recovery mechanism and a recovery protocol on top of it. You always have to do this. Basically, everyone has to do this. So you sit down one day and you say, I want to write durable object. And I'm going to spend 6 to 9 months writing a log, and then I can actually take a look at building a durable object. No, that doesn't fly. At least not in my world, it doesn't fly. So one of the things we'll be bringing to you in Indigo is a transaction-aware log interface, system.transactions.log. It's built in close cooperation with, it's built by the same team of people as the rest of system.transactions. They are closely coupled, and it is designed to give you a log that gives you write-ahead logging, a really well-known recovery protocol that you can leverage, a structure to work in, and it is built based upon the Longhorn Windows logging services. And what that means is it means performance, and it means the ability to coalesce your writes with other writes that are going on in the system. The whole goal of this is to give you a component that you can just use and start building from. Get rid of those first 6 to 9 months. So that's coming in Indigo, and you'll just be able to write to it. The second problem that I will have to deal with is if I want to offer multi-user access, multi-thread access to my resource, if it isn't really exclusive. Typically, I need to find a way to isolate the changes. That typically involves a lock manager, and the other component we'll be building as a min bar for Indigo is a transaction-aware lock manager that we're calling system.transactions.isolation. This does locking based on the transaction rather than the thread that you would see with system.threading. And it contains inherent support for two-phase locking. It understands two-phase locking, which is the typical way that you would deal with your isolation. Again, much like logging, the whole goal of this is to give you a very simple set of bricks to build from. They get rid of really the common goop that you have to build if you're going to build a complicated resource. What you should expect that we will do over time is build from those to provide higher and higher levels of infrastructure to make it simpler for you to do the common things that we expect you'll be doing for resources. That's really the end of the lap around what we're doing with transactions. The thing that we really want you to walk away with is that the programming model that you will use for an application or a resource shows up in Whitby. The pay-for-play programming, the pay-for-play performance model begins to show up in Whitby. Key pieces of it show up in Whitby. What we're doing is we're building underneath that. We're adding in more providers, more protocols. We will be extending out the pay-for-play model, and we'll be building up the resource infrastructure over time. But you can start in Whitby building from that model today. Oh, well, not today, because unfortunately it's not in the bits you get in the disk, right?
Actually, if they have long, there's a version of system.transactions which is within a stone's throw of what we just were using.
Right.
That's on the Longhorn
Right.
build. So if you install Longhorn, you get it. I believe Whitby VS .NET Framework,
Doesn't have
the
it.
one we're shipping with the PDC, doesn't have system.transactions, but by beta 1 it will.
Correct.
So when you get beta 1 of WIDBE, you'll have it for every platform.
And with that, we want to thank you. And I don't know if we officially have time for questions, but we'll certainly both be at Ask the Experts afterwards,
Yes,
Right.
which is now, I think.
which is now. So thank you.
Awesome.
Isn't that stuff good?